let's say we have 2 nanocoulombs, 1 meter, negative 4 nanocoulombs, 2 meters. It doesn't have to be exact same numbers. So now what are the questions? Well, we can say, what is the voltage created at the bottom right corner? What is the total voltage created there by these 3 charges? What is total voltage created at bottom right corner? And we could say at any other point too, just like we said, what's the electrical field here? Then we went to like here. What's the electrical field there? What's the electrical field there? You know, so we could also say any other point, bottom right corner or midpoint of top, midpoint of top side. So the idea is we can kind of do anywhere. Now, the other problem that we asked here, the other question we asked is, what is the force on this guy? Right? Electrical force on that guy. So then we took the force of this on there, it's like this. Force of this on there, it's like that. We broke it up into pieces. So now how can we ask something like that? How would we word that? Well, here it has to be, what's the equivalent of force for this chapter? Remember, electric field is to voltage as force is to electrical potential energy. You see? So if we're going to ask a force type question, now we have to word it in terms of potential energy. So how would we word that? What is the potential energy that the 3 new nanocoulomb charge has with both of these charges? I guess that's the best way to word it, you know. What is the potential energy of the 3 nanocoulomb charge with both charges? But we could word that question a different way. We could say, how much work does it take to separate the 3 nanocoulomb charge from the other 2 charges? That's kind of a more interesting way of asking it. This is kind of a dull question. This is more interesting, but they're actually the same question. You see, what is the potential energy of the 3 nanocoulomb charge with both charges? How much work does it take to separate the 3 nanocoulomb charge? Okay, what other questions? Oh, we could say, how much work does it take to separate all of the charges from each other? Or the other way to ask it is, what's the potential energy of the 3 charge system? What is the potential energy of the 3 charge system? How much work to separate all three charges. I mean, this is pretty much the same as this, except this one is asking for the two, well, you'll see what the difference is. It's very close, but slight difference. What other question? How about something like this? If you release all three charges, will they come and collide together? Come and collide together, or go out to infinity? If you release all three charges, will they come and collide together or go out to infinity? Find the final in either case. The final in either case. Okay, so this one is more talking about, so let's see, these two problems is assuming that the charges are fixed, and then I'm now going to separate them. You know, they're bound in their orbit, so they're not free to move. But then the question D is assuming they're free to slide. So then once you release them, do they come and hit each other, or do they repel each other? So you see the kinds of questions that the energy questions ask is quite different than the force questions, right? You can kind of tell. What other? Is there anything else? Okay, maybe one more even. E. You can say if a 2 nanocoulomb charge is released from very far away, from very far away, how much work does it take? Does it take? Which work does it take to bring it to the bottom right corner? Released from very far away. So if a 2 nanocoulomb charge is released from very far away, how much work does it take to bring it to the bottom right corner? Okay, so let's get our feet wet, jump in, and solve some of this. So what is the total voltage created at the bottom corner or any other point? Well, you're going to find that the questions in this chapter often are easier because voltage is a scalar and potential energy is a scalar. So you don't have to worry about direction. That's a big, big plus, right? So quite a lot easier. So then the voltage total created at that point is just going to be the sum of the voltages created by each one. So 9 times 10 to the 9th, 3 times 10 to the minus 9, over the distance from there, right? So that's just going to be 1 meter plus the voltage created by this guy. 9 times 10 to the 9th, negative 4 times 10 to the minus 9 over 2 meter. Now remember, with electrical field, if this was a negative charge, I would have said, oh, the electrical field is this way, and then this one, the electrical field is that way, right? Then once I put the numbers, I wouldn't have put a negative, because with electrical field, I analyze the direction of the electrical field by determining what charge it is. Once I go to the solving the problem, then I don't put the negatives again. But for voltage, voltage is just a number. This guy creates a number there known as electrical voltage, you see. And so this guy also creates a number there, you see. So then you have to add them. But the only way to tell the equation that this charge was negative is by actually putting a negative into the charge, because it has no direction, you see. So if you don't put negative here, how is it going to know that this charge was negative, you see? So with voltages and electrical energies, you have to put the sign of the charge, you see? So then what's this one? 9 times 10 to the 9th, 2 times 10 to the minus 9 over square root of, this distance is what? 2 square root of 5. Okay, and then this cancels. 27 plus negative 2, negative 18. Plus 18 over root 5. Right? $17. .05 volts. Okay. Okay, let's see that from that website. Because everything's usually worked out with electrical field. One, two, three. Oh, I put too many. Oh, yeah, okay. Okay. I was like, wow.
Yeah, it was your
I had too many negatives. Oh, there you go. Okay. Okay, 17.05. I love this feature. Oh my gosh. Everywhere on that line, the voltage is 17.01 volts. Wow. Wow. I could kind of go like different places. We could answer, for example, the second question was, what was the voltage at the midpoint between these? Where's the midpoint? Right here, right? Okay, you guys do that now. What's the voltage at the midpoint? Right there. Do the voltage of that, do the voltage of that, do the voltage of that. And you should get 19.55. So like that, 9 times 3 over 1 right? So this is 1 meter away. And then this is 9 times 2 over 1 meter away. And then 9 times -4. And then this distance is rad 2. See, lot easier than electric field. Lot easier, right? And then 19.54. Then you're going to do then over there. So now if we do the 10 again, ooh, everywhere there, the voltage is 19.54. I can go to like random locations. Okay, so everywhere here is 102 volts. Everywhere here is 45. So the voltage is going down, 19 volts here. This one is 16 volts. Now if we go this way, oh, beautiful feature. I love this. Oh man, physicist's dream come true. You see how computer science aids in science, Daniel? Wow, which program have they used? Now we could do any random location. Okay, the voltage here is -44 volts. So as we go towards negative charges, the voltage gets more negative. That's like saying the elevation goes below sea level, you know? Ooh. It's -3 volts. Well, let's find the equation for the 0 volt line. 0, 0, 0, 0. Yeah, somewhere over there. That's like 0 volts. So then if I go like that, oh, everywhere there, the voltage is 0 volts on this green one. You see? You see that? And then when you go here, now back to positive voltages. So all these are negative voltages, the ones that are here. You see? Anything inside of that 0 volts, the elevation is going down to negatives because this is a valley. You see, the negative charge represents a valley in the heights. And then these are like 2 mountain peaks, you see. So you see the elevations here are higher and here are lower. Let's see, how about somewhere here? Oh, you see, they're all bound to go through that area. So even if I go here, oh, you see, they keep going through there. It's like a squeezed elevation height right there. Isn't that cool? Wow. Now, if we draw the electrical field, what should happen? The electrical field lines are always perpendicular to the equipotential lines. You see how the electrical field goes out through here? So you see how they're always this is a 90-degree angle. So I'm just going to draw a rough picture. So if we draw like this, see, it kind of looks like that. So the electric field lines will look like what? See, the electric field will come out of this charge, go like that, see, perpendicularly. Let's see here. Yeah, it should go like this. See, you can't go bend and go into there because this is a positive. So it's going to go like this and start curving, and it should always be perpendicular. with arrows drawn. So that's the way to draw the electric field lines. Oh, I should draw it more perpendicular, like this. Then there's one coming out through here, perpendicular, perpendicular. So it's kind of like this, you see. This one you could draw like this. Let's see, what do you think this middle one would look like? See, it almost seems like it's coming, going into here like this. It's like going from here, bending, and then going into here. See, the way you have to do, always make sure that it's perpendicular. Even these eventually bend and go into the negative. So remember, there was another one that's like really like this. So then those guide you into drawing the field lines. You go like that, perpendicular, perpendicular, then you go like that, and then you go like that. Remember what I said, delta V is equal to, if you want to find the voltage difference between any 2 points, you say E dotted into dr. Right, and then I use this, or negative E dotted into dr. And then I use this to, I took a positive charge, and then I used that to find, I said let A be a point close to a charge and B be a point far away. So let's integrate that from A to B. Then I use that to find the point, the voltage of a point charge. But now let's switch that up. How do I show that the equipotential surface has to have the electrical field perpendicular? It is related to this. So here's what you argue. You say, let this charge be any weird charge, let's say 2Q. Let's say here's another weird charge, 4Q, okay, and then 3Q. So let's say this is an equipotential surface. In other words, the voltage here at A is the same thing as B. So by definition, equipotential surface is one where all the points have same voltage. And then in between here, there's some electric field line. You see, it could be random. You see, I want to argue that every single one of those electric fields is perpendicular to this surface. So I do this integral, VB minus VA, I get E dotted into dr, right? And then my whole point is that by definition, voltage of V is the same as voltage of A. This is an equipotential surface. So this is going to be 0. Okay. Well, the only way to ensure that the voltage there is the same as the voltage here is that the electric field has to be perpendicular. I mean, no. Yeah. The electrical field has to be perpendicular to my what? What's the dr? The dr is the path that I'm taking, you see, as I go from here to there. The dr is that. So the electrical field created by this charge distribution, if that shape is truly an equal potential, the electrical field has to be at every step of the way perpendicular to that shape. So even if that shape is not a circle, you see, so if you go back to the thing, you could say, oh, okay, let's just say this weird shape. The voltage here and the here is the same, right? The voltage here and here is the same. So now if I do that integral, all along the way, the electrical fields have to be perpendicular to the tangent line, the dr, along that path. That's pretty much it. That's it. Okay. Let's go to question B. What is the potential energy of the 3 nanocoulomb charge with both charges? So how do I find that? So then the potential energy that the 3 has with the 2 is going to be what? 9 times 10 to the 9th. And then what's the distance between the 3 and the 2? Let's see, the 3 and the 2 over the distance is 2 meters, right? Those are the top 2. 2 and the 3. Then the 3, what energy does it have with the negative 4? Okay, so then add to this 9 times 10 to the 9th, 3, negative 4. And then the distance is what? Square root of 5, right? Yeah, 5. And that's it. That's the potential energy. Let's see here. This one cancels this one. And then the nano is left. This one cancels this one. Nano is left. So then you have U is equal to, oh, the 2 cancels the 2. So 27 nanojoules. And then minus 27 times 4 over root 5 nanojoules. Okay. Oh, negative. Yeah, this is bigger number, 36 over. Okay, so the energy that the 3 has with both of them is a negative. Negative 21.299 nanojoules. Okay, so the question was put this way. What is the potential energy of the 3 with both charges? So then we would say negative 21 nanojoules. Now, how much work does it take to separate the 3 nanocoulomb charge from the other 2 charges? Is it going to take positive work or negative work? You see? So when something is at a negative potential energy, what does that mean? That means that it likes to be with the other 2 charges. Remember, things like to go towards more lower energy. The lower the energy, even below 0 is better, right? So if I drop something onto the ground, and if I dug a hole in the ground, something would prefer to go down and not only stop on the ground, but it would go through the ground, right? It would go towards lower energies. So that means if I let this go, it's actually going to get closer to these guys. It wants to get even more negative. Especially it would go probably more in the direction of the negative 4, right? It would go like that. So that means I'm going to have to do positive work to separate them, right? So then how much work do I need to do to separate? The absolute value of this, 21.299. I need to put positive work at least equal to the negative potential energy so that I can separate the 3 nanocoulomb charge at constant velocity. In other words, lift it up, you see? So imagine this calculator here has lower potential energy than when it's up there. So if I want to lift it, I do a work I do a work equal to the negative potential, the lower potential energy that it has on the table than up here, you see. So the work that I do has to be the absolute value of this guy. Okay. So be careful for the negatives in this chapter. That's where the test might get you. These negatives and positives, if the question is worded, what is the work required to separate, it would have to be positive here. Now, what if this energy was positive? What would the answer be? So when this is positive, what is this? Negative, right? In other words, if it's positive potential energy, it would be pushed outward, right, by the other two charges. So then I would be, if it's pushed outward, I would be pushing it in so that it goes out at constant speed to prevent it from accelerating. So I would be doing the negative work so that the 3 nanocoulomb charge goes out to infinity at a constant speed. So you're preventing it. In other words, it's like saying, if the calculator is here, how much work is required to lower it at constant speed? Well, negative work, because you're preventing it from dropping to the table, you see. So then the answer there would be negative. Okay, I think that's it for that question. Now, question C. What is the potential energy of the 3-charge system and how much work is required to separate all 3 charges? So how do we answer that? Well, we already know the energy that the 3 has. We already know the energy that the 3 has with this one and with this one. How about what other energies are there here? So all I need to do is add one more energy to this. These two have energy together. And then I'll know the energy of the 3-charge system, you see. So if you have 3 charges, how many energies do you have? This with this, that's 1. This with this, that's 2. And we already did that. And then this with this. If you had 4 charges, how many overall energies would you have? This with this, this with this, that's 2. This with this, or you know what you would do? You would start with the one that is 3. So you say this with this, this with this, this with this, that's 3. Plus this with this with this, that's 2. That's 5. And then one more, that's 6 energies you would have to add up, you see. So the more charges you have to do all the combinations. It's like combinatorics. So, this one, we just have to add this to it. So remember the answer was negative. So then I just have to add one more energy. 9 times 10 to the 9th. No, let's see, what are the charges? 2 and -4, right? I'm doing the top 2. No, I mean the left 2. 2 and -4. It's going to be what? 18. Ooh, -72. -72. No, nanojoules. Okay, then you just add this negative to this negative, and you get what? Negative 93.299 nanojoules. So you can see, if you weren't careful with the signs, if you had this positive and negative, you would throw out your final answer a lot. So you really have to keep pace and track of all the signs here. So the total potential energy of the 3-charge system is -93. So now how much work is required to separate them? So let's change this back to the correct answer, negative and positive. So the work to separate them is what? Well, the opposite of this, which is 93.299 nanojoules. 93.299. That's called the ionization energy, right? When you have separated these three charges completely, you have ionized that atom. You see. Ionization energy. D was if you release all three charges, will they come and collide together or go out to infinity? So then what will happen? If you release them, do they like being together? Or will they push each other out and separate out to infinity? It looks like they like being together. Why? Because their total energy was negative, right? Is negative 72. Oh, sorry, negative 90. The total energy was negative 93. No, they like being together. You know, so if we have to take a positive work to separate them, then yeah, that means they like being together. So if we release them, what will happen? They will come and collide somewhere in the middle. We don't really have to calculate where they collide, just as long as when they collide, they're moving like this. So let's assume they all have the same mass, 100 grams. And let's say they have the same radius, 0.1 millimeter. So what's going to be their final velocity when they collide? They should have the same velocity, right? So the good thing is we don't need to know even the direction that they're traveling when they collide, because this is an energy problem. Kinetic energy is a scalar, so we don't have to worry about that. So the way we approach these kind of problems is energy conservation. We're going to say the potential energy initial that they had is equal to their final potential energy times the final kinetic energy that they're going to have. Okay, so their initial potential energy was negative 93.299 nanojoules. Okay, what's their final potential energy going to be? It's the distance between their centers, right? When they collide. What's going to be the distance between their centers? From here to here, this guy, I think it's all going to be the same, right? It's an equilateral triangle. Again, I'm assuming that they collide at the same time, but maybe it's more complex than that. Maybe these two collide first, and then that one comes a little bit later on. So, but let's just take it simplistic. Let's say they all come, and then they collide, right? So what's going to be their potential energy? So this with this, what were their charges? Let me see, what were their charges? Where did I write that? Can't find it. Oh yeah, 3. So this one was 3. This one was 2. And this one was negative 4. Right, so then you have 9 times 10 to the 9th, 3 times 10 to the minus 9, 2 times 10 to the minus 9, over their distance, which is going to be what? Twice their radius, right? Twice their radius, yeah. 0.0002 meters, right? Because you got to take this 3 decimal places to the left, so that's going to be 3 zeros, but then double the radius. Okay, then plus the potential energy of this with this. Negative 4 times 10 to the minus 9. and then, so this with this, and then this with this. So you just have to make sure to do all the combinations. Negative 4 times 7 minus 9 times 2 times 7 minus 9. 0.0002. Plus, their kinetic energy is all going to be the same since they have the same mass. So it's going to be 3 times 1/2 mv final squared. Each of them is going to have the same kinetic energy. So you're saying 3 times the kinetic energy that a single one of them has. There you go. So this one cancels this one. This one cancels this one. This one cancels this one. Okay, so let's calculate that. $27 times 2 divided by 0.0002 minus 27 times 4 divided by 0.0002 minus 36 times 2 divided by 0.0002. Okay, so now you have negative 93.299 nanojoules is equal to negative 630,000 nanojoules plus 3/2, and then their mass is 100 grams. So 0.1 kilogram. So you see their potential energy was negative to begin with. Then when they got together, it became even more negative. You see, so always potential energy likes to go more negative. So then when you take this over there, it becomes a positive, you see, mathematically. So then that subtracts minus this. So then you say positive of that, then you do minus 93.299. Okay, so then 629,906.701 times 10 to the minus 9, right? Because the nano, you have to account for that. Then you have 3 as 0.1 v final squared. Okay, so then I'm going to say times 10 to the power 9 negative. Okay. Times 2 divided by 0.3, then square root. The final is, then I'm gonna, this is gonna be meters per second. So I'm gonna convert that to a more appropriate unit, would be 6.48 centimeter per second. That's a great unit for this, you see. So this is 0.0648 meters per second. Then you go 2 units to the right, 1, 2. 6.48 centimeter per second. That's how fast they're going when they collide. Really good problem there. So initial potential energy, the final potential energy between their centers, and then 3 times their kinetic energy. Okay, and then that's it. You solve for V final. Okay, last question asked what? If a 2 nanocoulomb charge is released from very far away, okay, I'm almost out of paper here. I'm going to get new paper. Let's see. 2 nanocoulomb charge, you release it from very far away. then it's assumed that it's coming, and we're going to kind of guide it so that it comes to that point. Maybe put a track here or something, like a railroad track, some kind of track. So is it going to want to come there, or are we going to have to force it to come there? So what was the voltage that we got at that point? Is it negative or is it positive? That's the key. Let's see, what answer did we get? 17 volts, right? 17.05 volts. And then what's the voltage at infinity? 0. Do positive charges like to go towards lower voltage or higher voltage? Right? So they like to go towards lower voltage, right? It's like saying, do pens like to go towards lower height? You see? So the answer is yes. So a positive charge is like a pen. Yes, it does. It likes to go towards lower voltage. So we're going to have to force this to come there. So we're going to have to push it. You see? It might, if we were guiding it this way, and the voltage here, remember, was negative. So then it would rush to get there, right? But here we're going to have to force it. So how much work would we have to do to bring that there? So then the work is its charge times the change in voltage that we wanted to experience. So we're wanting to experience a voltage change of 17.05 minus 0. The signs is what makes this chapter kind of hard. How do you know which one to subtract from which? What's the delta V, the final minus the initial, all these things, keeping track of those signs. So then we have, this is going to be times 2. So of course that's going to be 34.1 nanojoules. Okay, that's how much work we're going to have to do. So the answer would be to that question that it wouldn't want to come on its own. We're going to have to force it. And this much work is required to bring it to bottom right corner. Okay, how about if the charge was negative? How much work? So the question can be asked a couple ways. How much work would we have to do to bring it here so that it comes there at constant speed, right? So then it's trying to accelerate, so we're going to have to exert a force back. You see, we're doing negative work. It's like we're lowering the pen at constant speed. We're fighting against the gravity, so we're doing negative work, you see. So then the answer would be, we do negative 34.1 nanojoules. So you see here we put negative 2 if the charge is negative. You see, so we do this much work is required to bring it at constant speed. Bring it at constant speed. Now, you might ask, well, what if you don't exert that much work? What's the final velocity of that guy when it gets there? You see? So what if you allow it to freely get to that point? You see, there's so many varieties and variations of the questions, you see. So what if you allow it to freely get to that point? What is the final velocity? What is V final? You see, so we could approach it from this point of view again. U final plus K final is U initial. potential energy conservation. The potential energy that it has at infinity is 0. The potential energy that it has there at that point is its charge, nanojoules, times the voltage there, plus its kinetic energy. You see? So in a sense, in order for the signs to work, the initial potential energy is 0, and then it's gonna rush there to get there because it wants to get there. So the potential energy that it has there is its negative charge times the positive voltage that's there. You see? So then this one goes over to the other side and it makes the sign work out. Half times, let's say it's 100 grams again. 2 times 10 to the minus 9 times 30, no, times 17.05. Okay, and we can end with that. So 17.05 times 2 times another 2 from here divided by 0.1 times 10 to the power 9 negative, then square root of that. And then move it over, maybe move it over 3 times now. Then it will be 0.826 millimeter per second. So it's not going as fast. So if you allow that negative charge to get there by itself without friction, right? So then it'll be moving at that speed. You see, so then move the decimal point over 3 spaces, 0.826 millimeter per second. So keep track of those signs. Those are pretty tricky. Okay.